So, you're getting ready for the Unity Certified Associate Programmer exam, huh? Well, you've come to the right place. We are about to dive deep into the spatial math and input logic that you are absolutely 100% guaranteed to see on that test. Let's jump right in.
So, you want to code a homing missile? Or maybe make an enemy, chase the player around the map. Think about it. We've all seen this stuff. A zombie lurching towards you, a heat-seeking rocket, or even just a simple camera that follows your character. They all seem totally different on the surface, right? But underneath the hood, they are all running on the exact same piece of logic.
Believe it or not, all of that seemingly complex behavior, it all boils down to one simple, elegant, and, I can't stress this enough, absolutely critical formula. A single line of vector math. And today, we're going to master it.
All right, part 1, the GPS math. We're going to figure out how to calculate direction and speed. Basically, how does an object in your game even know which way to go? It's all about finding that direction. Okay, so the key idea here is something called a direction vector. Don't let the name scare you. In Unity, a vector is really just a piece of data that holds a direction and a length, or magnitude. For what we're doing, just picture it as an arrow in 3D space. That's it. It's got a starting point, which we'll call the source, and it points right at an end point, the destination. Our entire job is to figure out how to calculate that arrow. And here it is, the golden formula. This is probably the single most important thing you need to remember from this whole section. To get that direction vector, you take the destination's position and you subtract the source's position. That's it. Destination minus source. Say it with me. Destination minus source. You have to burn this into your brain. And hey, if you're worried about forgetting this under the pressure of the exam, here's a great little trick to remember it. Just think of the vector as an arrow. The destination is the pointy part, the head of the arrow. The source is where it starts, the tail. So the formula is just head minus tail. Super simple, right? And really easy to recall when you need it.
Okay, but what happens if you get it backwards? And trust me, this is a super common mistake to make. So what do you think happens if you accidentally type source minus destination instead?
Yeah, your object runs away. It goes in the exact opposite direction. Reversing that formula literally just flips the arrow around 180 degrees. So instead of a cool zombie that chases the player, you've accidentally coded a terrified zombie that runs for its life, which is kind of funny, but probably not the game mechanic you were going for. So, awesome. We have our direction. We're good to go, right? Well, not quite. There is a super common trap here that trips up almost every new developer, and you can bet it's a favorite for exam questions. I like to call it the diagonal speed bug. Okay, check this out. Let's say moving forward is a speed of 1, and moving right is also a speed of 1. Common sense tells you that moving diagonally, forward and right at the same time, should also be a speed of 1, right? Nope, wrong. If you remember your high school geometry, the diagonal of a square is always longer than the sides. It's the Pythagorean theorem in action. And what that means for us is that your combined direction vector is actually longer, so your character moves about 41% faster when going diagonally. It's a classic bug, and it makes your game controls feel really sloppy and unprofessional. So how do we fix this mess? It's so easy. One single word, dot normalized. It's beautiful. When you add dot normalized to your vector, it keeps the direction exactly the same, but it squishes or stretches the length of that vector so it's exactly 1 unit long. This gives you what's called a unit vector, and it means your speed is perfectly consistent no matter what direction you're moving. The key takeaway here, and write this down, always normalize your direction vectors before you multiply by your speed. All right, part 2, applying movement. So we've got this perfect normalized direction vector. Now, how do we actually use it to make something move? We're going to use a super common function called transform.translate. But to use it right, we have to talk about something called coordinate spaces. Okay, so there are 2 flavors here, space.self and space.world. Let's start with space.self because it's the default. Think of it like driving a car. When you hit the gas, the car moves forward, right? But forward is relative to where the car is facing. If you're pointed west, you drive west. Simple. Now, space world is completely different. Imagine your car is on a giant, invisible conveyor belt that only goes north. In world space, telling something to move forward always means move along the world's z-axis. Just think of it as moving north on a compass. Your car could be facing east, west, whatever. It doesn't matter. It's just going to slide north without even turning. That's the difference.
Okay, part 3, reading the controls. So we know how to figure out a direction, and we know how to apply that movement. The last piece of the puzzle is, where does that direction come from in the first place? Well, usually it's the player. For the exam, you've got to know about the input manager, and specifically the difference between getting smooth versus snappy input.
And this is a huge one for the exam, so listen up. You have two main ways to get input, Axis and AxisRaw. Input.Axis is the smooth one. Imagine a joystick. When you press the D key, the value doesn't just jump to 1, it kind of slides up from 0 to 1. And when you let go, it slides back down to 0. This is perfect for stuff that needs to feel like it has weight or acceleration, like a car or a walking character. Input.AxisRaw is the total opposite. It's raw, it's snappy. The instant you touch that D key, bam, the value's 1. The instant you let go, bam, it's 0. There is no sliding, no in between. This is what you absolutely need for games that demand razor-sharp, precise controls. Think 2D platformers, fighting games, or even just snappy menu navigation.
All right, theory time is over. You've seen the core concepts, now for the gauntlet. Let's run through a couple of exam-style questions and see if you can put it all together. You ready?
Okay, question 1. Picture this. You've got a cube sitting right at the center of the world, at position 0, 0, 0. We rotate it 45 degrees. Then we call one line of code, transform.translate 1, 0, 0. The question is, where does that cube end up in world space? Think really carefully about those coordinate spaces we talked about. I'll give you a moment.
Okay, you got your answer? Let's break it down. The absolute number one thing to remember here is that transform.translate by default uses space.self, local space. So that code is not saying move one unit along the world's x-axis. It's saying move one unit along your own local right axis. And since we rotated the cube 45 degrees, well, its local right direction is now pointing off diagonally into world space.
And that right there gives us the answer. When you move one unit along that new diagonal path, you end up at a world position of roughly 0.7, 0, 0.7. If you said 1, 0, 0, don't worry, that's the most common mistake. You just got caught thinking in world space instead of local space.
All right, next up. This one's about inputs. Imagine you're making a 2D platformer. Something that needs really tight controls. But you have a bug. Players are complaining that when they let go of the D key right at the edge of a platform, their character keeps sliding for just a split second and falls off. What's the most likely cause of that annoying slide?
Okay, let's think like a programmer here. The key word in the problem description is slides. The character doesn't stop instantly. That should immediately make you think about input smoothing. We know GetAxisRaw is instantaneous. It snaps to 0. So that can't be it. The culprit has to be GetAxis. Remember how it gradually slides back down to 0? Well, for those few frames where the value is, say, 0.3, then 0.2, then 0.1, your character is still moving. It's that tiny bit of leftover movement that's causing them to slide right off the ledge. So the answer is, you're using Input.GetAxis when you should be using GetAxisRaw.
And that's pretty much the whole story. So let's recap the big 4. Number 1, direction is destination minus source. Number 2, always normalize your movement vectors to fix that diagonal speed bug. Number 3, understand the difference between moving in space.self versus space.world. And number 4, know when to use smooth GetAxis versus snappy GetAxisRaw. If you can nail those 4 concepts, trust me, you are going to be in fantastic shape for any movement and input questions they throw at you on the exam.
So now you know exactly how to move things around with pure math using transform.translate. But you probably also know that Unity has a whole physics engine, right? With things like rigid bodies and adding forces. So the big question I want to leave you with is this. When should you use what we just learned, and when should you let the physics engine take over? Figuring that out, well, that's the next big step on your path to becoming a certified developer.